Welcome back to ECE 501B. Homework number 1 is due in a week. That's on the 5th of September. And we will not meet on Monday of next week. It's Labor Day. But you might watch or look on D2L. You might actually find some material that you can not miss a beat in terms of classroom content. Homework 2, I don't believe I've posted that yet, but that will be due a week from now. So in 2 weeks, homework 2 will be due, and that will be over chapter number 2 material, which we are beginning today. And today we are actually moving into one of the sort of paths associated with this class, and it's the finite dimensional path. That's in chapter 2. The infinite dimensional path is the second textbook, which is Frank's. And for what we've been doing so far, chapter 1, we haven't distinguished between finite and infinite dimensional vector spaces. Today what we want to do is start talking about what we mean by span, linear independence, now that we have numbers that we can, or finite numbers that we can deal with, the linear dependence lemma, and then dimension. And all of this, if we don't cover it today, it may be covered via other material on D2L in subsequent days. So look for that in the future. Chapter 2, relative to the big picture. Chapter 1, again, was the vector space, notions, ideas, direct sums. How do we slice and dice vector spaces to create subspaces, and then how do we put them back together? You can put them together uniquely via direct sums, non-uniquely by just adding subspaces, and likewise subspaces are not the same as subsets. But this is how it's organized, and now chapter 2 starts with the linear algebra material for finite dimensional vector spaces. That now starts with this notion of span. And here is what is meant by span. Given a list of vectors, let's say that vector list is v1, v2, up to v sub n, and that list of vectors is drawn from a vector space, then what we refer to as the span of that list is really representing the set of all possible combinations, possible linear combination of the vectors in that list. And that means then that we're going to mean, when we say span, what we're meaning is if we have the span of this list of vectors, v1, v2, up to v sub n, then what we're meaning by that, or it's defined to be some multiple a sub 1 of the first vector, v1, added to a multiple of the second vector, and these a's are coming from the field of numbers over which these vector spaces are operating. So a1, v1 plus a2, v2, these are scalar multiples or linear combinations of these vectors in the list, such that a1, a2, up to a sub n are coming from the field that we're interested in or that we're playing over. So when we say span of a list, and that list could be 1 vector strong, or it could be 3 vectors long, or n vectors long, then we're saying any linear combination, where can you get to in the vector space by linearly combining that list of n vectors? That's what we mean by span. To provide a visual for that, let's just think of this example, or let's consider the following example. Suppose that we're now given a list consisting of two vectors, v sub 1 and v sub 2, and we're living, the underlying vector space is R2. What's F? It's reals. So now we're playing over the field of reals, and we're looking at a vector space which is all of R2, and now we want to know what is the span of V1 and V2 of two vectors drawn from the vector space capital V. If we wanted to graph that, then V1 would be at 3, 3. And V sub 2 would be at 4, 5, where 4, the first coordinate, let's say, is the x direction and 5 is the y direction. And now I have to be better at drawing than I probably am going to illustrate, but there's now the two vectors, v sub 1 and v sub 2. And we want to know, relative to this two-dimensional plane, what's the span of those. And I think if you've had linear algebra, you already know the answer, but let's kind of walk through that or demonstrate why this now may, or the conclusion is, that V1 and V2 actually span the entire R2 space. They're almost aligned. If they were totally aligned, if they were exactly aligned, then what could we say about their span? Then we only have one dimension covered in that R2 plane, and that one dimension would be in the direction of the line that those two vectors are overlapping on. But here, since we have a little bit of variation or non-overlap, then we're good to go. But let's just show how that is consistent with this definition of span. Let's show that if we pick any, or we can find, you give me a point in 2 space, and I can find a coefficient a sub 1 and a coefficient a sub 2, which when used to scale V1 and V2, I can get you to that point that you just handed me. That's what we mean by it spans the entire space of R2. If it didn't, then I would only be able to get you to the span of those two vectors with any choice of A1 and A2. What I want to do in this solution then is try to illustrate that you give me a point and I can give you an A1 and an A2 to get you to that point, where A1 scales the first vector and A2 scales the second vector. So how can we now parameterize this span, the span of V1 and V2? We said that that's now a scalar multiple of the first vector plus a scalar vector of the second vector, such that A1 and A sub 2 are drawn from the real line, or the field of real numbers. Plugging in particular, or the particular vectors that we are using in this example, V1 was 3, 3. We're scaling that but with A1, and A sub 2 scales V sub 2, which was 4, 5. Again, for A1 and A sub 2 belonging to the field of real numbers. Or we can now push those scalars through and combine the vectors, sum the vectors, or add the vectors, and we now see that we have 3a1 plus 4a sub 2 forming the first coordinate, or the first component of our 2 vector, and we have 3a1 plus 5a2 forming the second component, or second coordinate of our vector. And now again we can say, can we, given some generic point, let's say that now somebody says, let me be given a z1 and a z sub 2, and I want you now, if you're saying that you can get me anywhere in R2, then you better be able to, or I better be able to find an A1 and an A2 to do that for any point z1, z2 that you give me. And that now really, depending on how you think, but if you've had a linear algebra class, you're going, oh, this is just a matrix inverse problem. You're saying, oh, now z1, z2, does that, in fact, can I get you the z1 and z2 if I now, or by the choice of an a1 and an a sub 2? And I can fill in, or I can populate this 2 by 2 matrix with the coefficients. z1 is now 3 a1 plus 4a sub 2, and z sub 2 is 3a1 plus 5a sub 2. And if it's possible for me to give you a's given z's, then this matrix better have an inverse. And if it has an inverse, if you remember your linear algebra, it will have an inverse if the rows are linearly independent, or if the columns are linearly independent, or the determinant is 0. But this book, Linear Algebra Done Right, doesn't give us determinants until the very end chapter. That's how you do linear algebra right. Is you wait until the end to worry about determinants. But let's go ahead and invert that matrix. A1, A2 is now found by 3, 4, 3, 5, and hopefully by inspection you can see that the columns are linearly independent. They're not the same. 3 is maybe a multiple of 4, but it's not the same multiple to get you 5 from 3. So 3, 3, and 4, 5 are not in the same direction. And do you remember the trick for a 2 by 2 matrix to invert it? 1 over the determinant, so we have to jump to the back chapter. No, we'll just know the determinant of a 2 by 2. So now we have 1 over the determinant, which is 3 times 5 minus 3 times 4. The product of the diagonals minus the product of the off diagonals. That's 1 over the determinant. And then what do we have? Flip and negate some stuff. What do we flip and what do we negate? Well, we interchange the diagonal elements. The 3 and the 5 just switch places. So the 5 comes here. It was 2, 2. Now it's the 1, 1 entry. And 1, 1 becomes 2, 2. So we just interchange the diagonals and we negate the off diagonals. So we negate 4 and we negate 3. And now we've essentially found the relationship given a z vector, z1 and z2, I can now calculate from this formula the a's. The denominator is now 15 minus 12, or 3. And if I divide 3 into the bottom row, that's nice and clean, isn't it? Those were 3's. My bottom row is nice. My top row, not so much, but it's still 5 over 3 and minus 4 over 3. Or if I want A1 and A2 from the z's, I'm just going to scale z1 by 1 2/3 and add that to 1 or subtract from that 1 1/3 z2. And then I'm just going to take z2 and subtract z1 from it to get my a sub 2. That's how you would do it mechanically. If every problem you're faced with, you like to just invert a matrix. If you don't, yes, question? The question was, do I want to see the steps? You need to on an exam. Or can we just use the sum 2 letters calculator? Okay, TI. They're a local company, and they've actually have their pictures all over our room upstairs in the conference room, so we can say Texas Instruments. If you have a calculator, you can, but I want you to set it up. Set up show the first line, and then say with TI or with calculator, and then you can give me your answer. Is that okay? Hopefully that won't be the big problem with your exam. If you don't have a calculator that does that, just giving me that and saying, oh, I just need to invert the matrix, and then I'll give you A1 and A2, that's fine. And then keep going with the other part of the exam, and if you have time, go back and fill in the steps. Is that okay? All right. So if you don't have the calculator, and if you don't think in terms of inverting a matrix or setting it up in terms of a matrix, maybe you just solve it in terms of 2 equations and 2 unknowns. And you know z1 is equal to 3a1 plus 4a2, and z2 is 3a1 plus 5a2. You could solve it that way. So now we have z1 is whatever I just said, 3a1 plus 4a sub 2, and z sub 2 was 3a1 plus 5a sub 2. And now if we compare those, we see that we have 3a1 in both equations, so my comparison is going to just take the difference between those, and I can see then that z1 minus z2 is equal to 4a2 minus 5a2, or minus a2. So that now, with that relationship, I see that a sub 2 is just z sub 2 minus z sub 1. And now I can use that relationship for a sub 2 in terms of the z's in either of the 2 relationships above. If I apply it, let's say I apply it in the top one, then I know that z1 is 3a1 plus 4a sub 2, but a sub 2 is just z2 minus z1. So that I now have 3a1 plus 4z2 minus 4z1 and I have 5z1 minus 4z2 is 3a1. Pushing all the z's to the left, and that now allows me to say that a1 is indeed 5/3 z1 minus 4/3 z2. And I did that without inverting a matrix. I just said, oh, I have two equations in two unknowns. I need to solve for the two unknowns, which were the a's, a1 and a2. What does that say? Well, either of these approaches, now I have a strategy. Given a z, z1 and z2, I can now give you the a's that are required. And the a's, remember, were the scalar multiples of v1 and v2 that are needed to get you to that point that you were handed for z1 and z2. Therefore, for any choice of real numbers for z1 and z2, the span of those original vectors that we started with, v1, v2, will allow you to realize that point z1, z2 in the 2 space R2. So we can fill the entire plane. If we wanted to do that for a particular point, we can. Suppose somebody says, I want you to arrive at 1, 0 in the 2 plane by some linear combination of v1 and v2. What is that linear combination? Now you have the equations to do that. Here, we want z1 to equal 1 and z2 to equal 0. And we have formulas for a1 in terms of those z's. Whoops, where'd that 4 come from? Somewhere in outer space, maybe. But I think it was 5/3 z1 minus 4/3 z2. So now a1, I just am scaling v1 by 1 2/3. And a sub 2 was z2 minus z1, or 1 minus 1. A sub 2 now tells me I just need to go in the opposite direction with the same dimensions as v sub 2 started with. Or that point that I was handed, 1, 0, which really says walk one step in the x direction and don't go in the y direction. How do I get there? Using the v's, I take 5/3 of v1 and add to that minus 1 of v sub 2. Don't ask me why I'm going from brackets to square, or to non-bracketed or parentheses, but just was easier. Is that clear? So now let's look at what happens if we're given an arbitrary list of vectors. What does that produce? So statement 2.7 in chapter 2 says span is the smallest containing subspace. So if somebody says, what's the span of these vectors, then you're really saying, what's the smallest subspace that is spanned by that list of vectors? Or the span of any list of vectors in the vector space V is in fact a subspace of V. In our last example, what was the span of our V1, V2? What was the subspace that it spanned? It spanned all of V, didn't it? V was R2. It was the full. And we know in R2 the different kinds of subspaces. There aren't that many possible. Well, there's an infinite number, but they all fall into a nice clean group. The zero element, the full space, and what's the other possible subspace type? X-axis, Y-axis, any line that goes through the origin. That's the other type of subspace. And we had what? We had two lines that were not overlapping, and that was then capable of spanning the full space. Suppose we wanted to prove this proposition, that the span of any list of vectors in V is a subspace of V. If we want to show that something is a subspace, what is needed to show a subset of V is a subspace? If I have a vector space that's full of vectors, and now I pull from that vector space a list of vectors, that's really what I'm saying. How do I show that that subset, those vectors of V, form a subspace? How do we show something is a subspace? What did we talk about last time? I think we talked about it, didn't we? Did everybody hear those three things? There's three properties that we need to verify to show that a subset is a subspace. The zero element, closed under addition, closed under scalar multiplication. Why do we only have to show those three? There's more than three properties for a subspace, is there not? The others, they just kind of inherit the properties because they're a subset. So they just kind of get those for free because they're coming from the underlying vector space. They inherit the other properties. That's why we only have to show these three. So let's suppose then, what did we have? Let's suppose U is a subset of the vector space V. then we need to show that U also satisfies those three properties. One, that the zero element is in U, the subset, or we have this additive identity. It's closed under addition. Vector addition, where vectors are the elements of the vector space. It doesn't have to be a tall, thin column of numbers. It's just a vector. A vector could be a matrix. It could be a polynomial of the vector space. And then 3, it's closed under scalar multiplication. Let's see what happens if we're just given. Suppose we're given now a list of vectors. And let's call that list W. So we have V1, V2, up to V sub n, and those vectors are coming from our underlying vector space V. And we want to show that W, or the span of W, is a subspace. We didn't say that it has to fill all of V, it just has to be a subspace of V. So the span of W how is that defined? Or how do you state that in words? All linear combinations of the vectors in the list, right? That's the span of W. So this is equal to all linear combinations of the vectors, let's say, V sub I in W. So first we need to show that it's actually a subset of V. And then if it is, then it just has to have these three properties. So we'll first show that it's a subset. All elements or this is really all vectors in the span are elements or vectors of the underlying vector space. That's where we pulled them from. Since V is closed under addition and scalar multiplication. And that's really what we need to do a linear combination, is scale and combine. Combine by addition. The operations used in forming linear combinations. So the span is in fact a subset of V. and it's actually non-empty since it's a list of n. Span of W is a non-empty subset of V. We now have a subset. Let's see about the other three properties. First, can we take those vectors and create the zero vector by some choice of scalar multiples? That's pretty easy, isn't it? Just make all your A's 0. So now we can get the 0 element by saying, oh, we have 0 times V1 plus 0 times V2. Are those zeros the same on the left and the right of the equal sign? The one on the left is the 0 element. The ones on the right are scalar zeros, aren't they? So there we have that is an element of V, and so now we've shown that 0 is in the span of W. We know V was a vector space, so we know the 0 element is in it, and now we've shown that a linear combination of the V's, which is the span of W, belongs to V. So now we know that we have the additive identity in the span of W. Now we need to show that it's closed under addition. So let's take W1 and W2 to be contained, or elements, in the span of W. How would I write W1 if it's in the span of W? It's a linear combination of the V's, isn't it? So now to make the notation a little more consistent, I was saying A1 times V1, A2 times V2, but now I want two vectors, or two elements, W1 and W2, so let me sneak a 1 and a 2 in there as well on the coefficients. So let me say that this is A11 times V1 plus A12 times V2, etc., down to A1n times Vn. Did I start with Nevada or Michigan number of vectors? Nevada? Okay, so my n's are consistent, aren't they? And if we use that same notation, the linear combination of V's to make up W2 is A21 V1 plus A22 V2 A2n Vn. Let's now add W1 and W2. That gives us A11 plus A21 V1, A12 plus A22 V2, and now what can we say? Well, this is, what do we know about these A's? Where did they live? In a field. And what do we know about a field? It's closed under addition, isn't it? So now we know that all of these coefficients belong to the same field. A11, A21, we could just call that alpha. What do I want to call it? Alpha 1 to get back to just one subscript. This we could call alpha 2, and this we could call alpha sub n. And all of those coefficients, or all of these coefficients, are elements in our underlying field, since the field F, or the symbol F, is a field, or it's symbolizing a field, which indeed is closed under addition. Therefore, W1 plus W2, we've just shown is in a linear combination of the V's, or is an element in the span of W, or now the span of W, that subset is closed under addition. And I think you can anticipate what I'm going to do next. Do something similar with scalar multiplication. So we've found that span of W is a subset. We've shown that it contains the 0 element. That was 2. 3 we just concluded. It's closed under addition. Let's now go ahead and finish this with 0.4 to show that it's closed under scalar multiplication. So let's now just take one element from the span of W, and let's pick a B from our field. So if W1 is in the span of W, then we have A1 V1 plus A sub 2 V2 plus A sub n V sub n. And B times W1 is just B A1 V1 plus B A2 V2 B A sub n V sub n. But all of these coefficients, these B A sub j's, are elements of F, since B is in F and all the A's were in F. But the BAG's are elements in F, since F is a field. And since it's a field, it's closed under scalar multiplication, which is what we're needing for the B A sub j's. So F is a field and is closed under scalar multiplication. Thus, this is a linear combination of the V sub i's, which says then that the span of W, which is just a linear combination of the V's, is closed under scalar multiplication. And now we've shown all three parts, plus the fact that it was a subset. Or we now can say that the span of W is indeed a subspace. Span of W is a subspace of the original vector space V. What are some takeaways that we can now sort of collect? One is that the span of a list of vectors is the smallest subspace that contains these vectors. And there is a relationship now to this subspace sum notion. There is a relationship to the concept of subspace sums. If W is a list of all vectors in, let's say, subspaces U1 and U sub 2, then what can we say notationally about the span of W? How did we represent combinations of subspaces? So now, if we want to be all-encompassing or more encompassing, do we want unions? Do we want sums? We want sums, don't we? So now we want the span of W is just the sum of those two subspaces, U1 plus U2. If W is the list of all vectors in those subspaces, U1 and U2, then we can say that the span of W is equal to U1 plus U2. However, we will soon see that maybe we don't have to keep collecting all vectors. However, we will soon see that this spanning set is able to be reduced in terms of the number of vectors that we need. So let's introduce some terminology. If the span of, let's say, V1, V2 up to V sub n is in fact filling up or spanning the entire vector space V, then the vectors v1, v2, v sub n are said to, this is the terminology, span v. So if the span of v1, v2 up to v sub n equals v, then we just say the span of the v's, or I'm sorry, they span v, that list of vectors. And here, that list has how many, or what kind, or what quantity of vectors in it. N, which is finite. So this now leads us into finite dimensions. Finite dimensions. A vector space V is said to be finite dimensional if it is possible to construct a finite length list of elements or vectors that span that vector space or span V. If we can now find a finite list of n vectors, n is 3, n is 10, then we know the dimension of that vector space V, if that list spans V. That also now allows us to start talking about linear independence. Which is definition 17 in chapter 2. The vectors in a list, let's say v1, v2, up to v sub n, are said to be linearly independent if the only combination of those n vectors that equals the zero element is the one combination where all of the coefficients in that linear combination are 0. You give me a list of n vectors and now say, oh, how do I linearly combine those n vectors to get the 0 vector? If the only way that I can do that is by scaling each of those vectors with the 0 scalar, then I know that those n vectors are linearly independent. Or that is a1 v1 plus a sub 2 v sub 2 plus a sub n v sub n equals 0 if and only if, or if that implies a1, a2 up to a sub n are all 0. Another way of saying that, or this is equivalent to saying none of those n vectors, none of the vectors that are in our list, in the list, can be written as a linear combination of the remaining vectors, if they're linearly independent. So this is equivalent to saying none of the vectors in the list can be written as a linear combination of the remaining vectors. A corollary to that statement or proposition that said that the vectors in a list are linearly independent if all the coefficients are 0 in order to get the 0 vector, a corollary is that if a list of vectors if you already know that it's linearly independent, if a list of vectors is linearly independent, then none of these vectors can be written in terms of the other vectors. Suppose we wanted to prove that corollary. We have different ways of doing it. This is a conditional, isn't it? It's basically saying if a list of vectors is linearly independent, then none of the vectors can be written in terms of the other vectors. If A, then B. A is we have linearly independent vectors. B is we can't write them in terms of any of the other vectors. We can't write any of those vectors. Let's do this by the contrapositive. Let's assume not B. The contrapositive strategy then is to say we need to show not B implies what? Not A. That's logically equivalent to A implies B. So now, based on this corollary, What is not B? One of the vectors can be written as a linear combination of all the others, right? And you'll see this written many different ways, but let's now say that suppose, I'm going to write it in a way that you probably wouldn't see it in a standard proof. Suppose the list of vectors are labeled such that not B is really V sub n is equal to A1 V1 plus A sub 2 V sub 2 plus A sub n minus 1 V sub n minus 1. With at least one of those coefficients not equaling 0. So that's what I'm meaning by not B. And I've labeled them in such a way that the last vector in the list, V sub n, is the one that's the linear combination of the others. How might you have seen this written in a more formal source? You might, instead of say, suppose the list of vectors, they may say, without loss of generality, or they may say WLOG, without loss of generality, let V sub n equal, right? They may not say, suppose the list can be rewritten or labeled. They may just say, without loss of generality, let V sub n equal. And behind the scenes, you're saying, okay, sure, I can relabel my vectors such that the last one, V sub n, is some linear combination of the first n minus 1. Just saying. So now we have V sub n written this way. What if I take away V sub n from both sides of this equality? What if I now say V sub n minus V sub n on the left? What's that give me? That gives me 0. What do I have on the right? Well, I have A1 V1 plus A sub 2 V2 plus A sub n minus 1 V sub n minus 1 minus V sub n. Or writing that again, just rewriting it to, well, I'm thinking. Let me just rewrite it and maybe something will pop out. Now I've said that A1 V1 plus A sub 2 V sub 2 plus A sub n minus 1 V sub n minus 1 minus V sub n is equal to 0. But what do I know about the left-hand side? The coefficients on the left-hand side, based on my earlier fact. I know 1 is not equal to 0. I have a minus 1. And I also know that one of these other A sub j's is not equal to 0. So I have at least 2 that are non-zero, and they're summing to 0. Yes? Why do I need A sub I? I don't need what I'm saying, I don't know if I'm clear, but here I know that V sub n is some non-zero right-hand side. So I know that one of those A's, A1 through A sub n minus 1, is non-zero. So now Vn is not 0. So we're assuming Vn is not 0. because we started with a non-zero set of v1 up to v sub n. And now we have hopefully demonstrated that the left-hand side, we have a couple of coefficients that are non-zero, with at least two coefficients being non-zero. But what does this sort of mean? How do we connect this? I have v1, a linear combination of v1 through v sub n equaling 0, and I have some non-zero coefficients. If v1 through vn were linearly independent, all the coefficients would have to be 0, wouldn't they? So this is really saying not A. Is that? So this is really saying not A. Or now we know that the list of vectors is not linearly independent, it's linearly dependent. List of vectors is linearly dependent, and that's what we needed to show. We needed to show that not B implied not A, and we've now shown that. Thus, since not B implies not A, which is the contrapositive argument, and because that's logically equivalent to if A then B, then we can conclude A implies B, which was our original corollary, or the original corollary is in fact a true statement. Which was what? Let's remember what we were saying. If a list of vectors is linearly independent, then none of those vectors can be written as a linear combination of the others. Can I go up a little bit? I don't know. It depends on what that means. So there's no difference between this statement and the corollary. So what we were showing is really that from the proposition, we sort of concluded that this list cannot be written as, or any vector in the list cannot be written as a linear combination of any of the other vectors. Oh, that's a corollary. So a corollary is really just a secondary conclusion from a proposition. And so we just went ahead and formally said, let's state that as a corollary. So we basically just said the same thing from one statement to the other. But in the bottom one we said, let's just call it a corollary. Is that okay? Now, let me ask the following question. Can a list of vectors, can a list of vectors containing the additive identity be linearly independent. And since that's 50-50 odds of getting that right, I'm going to up it a little bit and say why or why not. So I'm not going to just let you say yes or no. I want you to justify your answer. So can a list containing the additive identity be linearly independent? Well, apparently this thing, there was some overlap there, so those weren't linearly independent, those A's, if you saw that. If you had your head down, you missed it, but it's not worth repeating. Hopefully it won't repeat. So now I want to get your answer, not right now, but at the count of 3. If you think the answer is yes, I want to see a thumbs up close to your body. And if you think it's no, then give me a thumbs down close to your body. The reason it's close to your body is I don't want you looking around and going, which way's my thumb? Which way's my thumb? So if you're at home, you can sit in front of a mirror and watch and see which way you're putting your thumb. So at the count of 3, I want you to give me your answer to this question. Can a list containing the additive identity be linearly independent? 1, 2, 3. Oh, and if you don't know, I guess you can have a horizontal thumb. So I'm seeing some ups and some downs. So we're not quite clear on this, are we? So how would we justify this? If a list what does it mean for a list to be linearly independent? Can we just linearly combine those vectors and do what? Say something about their coefficients? What if I gave you a list that was A1V1 plus A2V2 plus ... plus A sub n 0. And if this list is going to be linearly independent, one way of quickly figuring that out is to say, oh, the way to get the 0 element is to combine these vectors to give me the 0 element. But if they're linearly independent, what do we know about how those have been combined? What has to happen with those coefficients? They all have to be 0. What's this? Well, you can't see that at home, so I was actually trying to highlight that. What do we know about that particular term in our sum or our combination? Does it matter what A sub n is? Can I pick it to be something other than 0 and still get 0? Yes. So now what's your answer? No. Because, here's our justification, this coefficient, that can be anything we want, and it can definitely be not 0 and still give us 0 in that combination. So this can take any value without affecting the sum. And we need all of those coefficients to be 0 to be linearly independent. And now we have one that's not. So any list that contains the additive identity is by default not linearly independent. And we'll pick up there, or you'll pick up there on Monday or sometime with the linear dependence lemma, which is now, how do we talk about, we've talked about linear independence, let's talk about linear dependence.